Okay, this is a video about carbonyl compounds, or we often refer to them, of course, as aldehydes and ketones. And the two functional groups are usually associated very much together. And it's a quite small topic, but there's some very important and regularly asked facts within it. So first of all, let's just have a little look at what the spec says. Roughly, it's two things: the reactions of carbonyl compounds and the characteristic practical tests and the sort of detail of the practicalities, which is quite often asked as well. Okay, so first of all, the carbonyl compounds, aldehydes and ketones, make sure we can tell the difference between the two. They both possess the carbonyl group, the CO double bond. Well, of course, this is a carbon-oxygen single bond, sigma bond, with two localized electrons between the two atoms and an additional two electrons from the p orbital of the carbon and the oxygen. So these two create, of course, a pi bond. So yes, it's a double bond like an alkene, but here's the big difference. The carbonyl bond is polarized, of course. Electronegative oxygen pulls the electrons in the pi bond and the sigma bond towards itself, so giving the carbonyl group a delta plus on the carbon and a delta minus on the oxygen. This means that they are readily attacked by nucleophiles, unlike the alkenes, which of course are attacked by electrophiles. The simple difference between them is the location of the carbonyl group. The carbonyl carbon is always carbon number 1, that is at the end of the chain of carbons in an aldehyde. The carbonyl carbon is not at the end anywhere else but the end in a ketone. So quite simply, the endings for the molecule names, aldehydes, of course, end in al, such as methanal or ethanal or propanal. And the ketones ending, of course, is one, pronounced O-N-E, spelt one. Here is an example. This is the aldehyde propanal. As you can see, 3 carbons, the CH3, CH2, CHO. We write the group as CHO rather than, of course, COH, which would misleadingly look like an alcohol. Here is, of course, 2-carbon aldehyde, and this is ethanal. Notice the carbonyl carbon is carbon number 1, always the end one. Whereas the ketones, on the other hand, they will use a different carbon, and that means, of course, there has to be a minimum number of carbons in a ketone of 3, because we've got to have the carbonyl carbon in the middle, because there must be carbon bonds, there must be carbon atoms bonded either side of the carbonyl group to create a ketone. So this is the smallest ketone of 3 carbons, and this, of course, is propanone. This is otherwise known as acetone, or is nail varnish remover, and is quite a useful industrial chemical. This one is called pentan-2-one. Notice we need the locating number 2, and that's the lowest possible locating position for the carbonyl group. We could, of course, have the structural isomer, which is pentan-3-one, with the carbonyl group right in the middle. That would be what we call a symmetrical ketone, if we've got the same number of carbons either side of the C double bond O. Well, of course, pentan-2-one, as you can see, we've got 3 carbons on the left and 1 carbon on the right. So this one is an unsymmetrical ketone, and of course, this is the basic reason why we have to put the number 2 or number 3 in the name. Now, the oxidation of the aldehyde and ketones follows on, remember, from the oxidation of alcohols. Primary alcohols oxidize to give aldehydes. Secondary alcohols oxidize to give ketones. Now, there is a further stage of oxidation which only the aldehydes can do. Now, this is really important. Aldehydes can be further oxidized to carboxylic acids, but ketones cannot. The oxidizing agent we choose to use is this one. It's called acidified dichromate for short, or acid dichromate for short. The actual combination of chemicals could be either sodium or potassium dichromate, there's the formula, and dilute sulfuric acid. And between them, the two chemicals produce an orange-coloured solution. Now, in the reaction, we're allowed to use the O in square bracket symbol to represent the oxidation reaction. So here is the example of propanal, 3 carbons, being oxidized, of course, to propanoic acid. Notice the insertion of the additional oxygen between the carbonyl carbon and the aldehyde H. So in between these and those, we now insert the extra oxygen. So that makes a more oxidized functional group, the carboxylic acid. And of course, that's the highest priority functional group and always goes on the end of the name. Ketones, on the other hand, do not oxidize in this way. We are not able to insert another oxygen between the carbon and either side carbons of the carbonyl carbon, because of course that would break up the carbon skeleton. By inserting between the seed carbonyl and either neighboring carbon would break up the carbon skeleton, so that doesn't happen. So the reduction reaction of aldehydes and ketones, of course, is the reversal of the oxidation, and the reagent of choice we use for this is NaBH4, sodium borohydride. There are other reducing agents such as lithium aluminium hydride, but that's not on our specification. This particular chemical is dissolved in methanol and water and is a very good reducing agent. The tetrahydridoborate ion BH41- provides the hydride ions, and it's common practice to represent the reducing agent as a H in square brackets, just like we did with the oxidation O in square brackets. It does allow much easier balancing of the reduction equation, as you'll see. So here we go, we've got propanal this time on the left, and the two H's will reduce it down back to propan-1-ol. Of course, aldehydes will always reduce to a 1-ol. Now, as you can see, all that's happened really is the two hydrogens have been returned. One to the oxygen to make it an OH, and the other to the carbonyl carbon to make that a CH2 group. Ketones, on the other hand, when we insert the same two H's, again, one on the oxygen to make an OH, and this, of course, is the secondary alcohol, and this one is propan-2-ol, and the second H takes the bonding position on the same carbonyl carbon. So we return the two H's that were removed for, of course, the oxidation. Now, the reactions of aldehydes and ketones reduced from form primary and secondary alcohols, and this is very important as a mechanism. Using the reducing agent, here is the H- hydride ion, and as you can see in the first step, a curly arrow from the lone pair on the hydride ion is donated in a bond formation to the carbonyl carbon. And of course, this has to be nucleophilic attack because the hydride has electron pairs, or is a lone pair donor, and the carbonyl carbon is electron deficient. And so if we carry on the mechanism, of course, then the next stage of the mechanism is the curly arrow movement from the carbonyl bond towards the delta negative oxygen. Now that's a bond breaking movement, so that now leaves the carbonyl carbon oxygen with now just a single bond. So the reaction is completed by the oxygen on the carbonyl carbon oxygen group giving a lone pair to either H plus, or as I've shown here, a water molecule. Now, a water molecule present from the aqueous solution or a H plus ion from the same solution. So there is the complete mechanism. And of course, it's important you know this and learn that, and you're aware of the curly arrow movements, the charges, the lone pair. Notice the lone pair on the O, the minus charge on the O, the minus on the hydride ion, And of course, the mechanism must be practiced. So this is nucleophilic addition and is really important as one of your 5 learnable mechanisms. Okay, so if we carry on the reaction, and this time the alternative reaction reagent is the reaction with potassium cyanide. The Cn- nucleophile this time is generated either from potassium cyanide or the reaction of the potassium cyanide with a dilute acid. HCN, the product, is extremely poisonous, and so we tend not to use that. We tend to use the mixture of the salt potassium cyanide and acid during the reaction. So here's the equation for the formation. As you can see, the potassium cyanide ionizes to give, in acid solution, potassium ions and the more important nucleophile, the cyanide ion. So rather than the H- nucleophile, this is the Cn-. Same mechanism, curly arrow from the Cn- carbon to the carbonyl carbon, and this of course followed by the movement of the electron pair out towards the oxygen. So this creates our product where we create a molecule which is called a hydroxynitrile. It's not quite finished yet. We have the same operation to return the H plus either from water or from H plus from the HCN formation to give us an OH group on the carbonyl carbon that was. So if we look carefully at what the carbonyl carbon has now become, it's now gained the CN group and is also an OH. The carbonyl oxygen, which is now OH, is the hydroxy part, and the nitrile is the name of the carbon skeleton. So if we look carefully at this particular one, we count the carbons 1, 2, 3, 4. So this one is 2-hydroxy butane-nitrile, which is the correct naming for the nitrile. It goes on the prefix as the hydroxy relegated to the front of the name, and the suffix nitrile is at the end, of course. So here is the reaction, and this is the product of the formation. Now, in some cases, you can see the rather important idea comes out here. Keep an eye on the carbonyl carbon that was. It is now a carbon atom with 4 different groups attached to it. We call that a chiral carbon, and that leads to the property of optical isomerism, or the formation of enantiomers, as we'll see in a later topic. Okay, so the idea with the potassium cyanide reaction, here's the mechanism again one more time. To finish the reaction off to give the hydroxynitrile. Another important feature of this, of course, is the formation of new carbon-carbon bonds. So here is the original carbonyl, which has 3 carbons, and now the hydroxynitrile has got 4 carbons in the longest chain. So it's a really important example of carbon chain formation. Now, the last part of these is principally 2 practical aspects. Tollens reagent is a chemical test which we use to distinguish aldehydes from ketones. Tollens reagent is a colourless solution made by reacting silver nitrate with dilute sodium hydroxide and then dissolving the precipitate with ammonia. The product of it, Tollens reagent, is a diamine silver 1 complex ion, as you can see, and when heated with an aldehyde, we get a very famous silver mirror product. The test tube has a silver lining, literally. The second test that we need to look at is the test which determines the presence of either aldehyde or ketone. Either type of compound will give this orange precipitate with the 2,4-DNP or Brady's reagent. There's an example of what the orange solid looks like. Now, by collecting the solid and purifying it, we do this by dissolving the solid in a minimum volume of hot solvent, such as ethanol. We cool it, allowing crystals to form. After collecting the crystals by vacuum filtration and drying them, we can measure the melting point of the crystals. The melting point is a precise indicator of which carbonyl compound